And let's start. I hope the other guy who is on MS Teams can hear me and see the slides. This is required just to make sure the recording is working. Okay. There's no way of testing, but in any case, we're recording from this side. Just check it once. So in the meantime, thanks a lot for joining. You are under no compulsion, and anyways, we started around 20 minutes late. So we'll start go till 12:20. Feel free to leave within. I understand that you already have scheduled things, and this will be anyways be available in your Teams. This is just think of a pre-recorded lecture. And again, I'm grateful that you can join on a Sunday morning. I'm pretty sure that you had plans, so thanks for that. Okay, perfect, good. So let's start then. So today we will talk about, hopefully, two main final concepts of your OS class, specifically in file system. One is how to allocate free space to a file. You want to create a file, and you have a bunch of free spaces. How can you do that? And we'll talk about how to manage that block of free spaces. So let's start with assuming that you have a bunch of free spaces, you have a file to create, how to allocate that free space, those blocks, to files. Specifically, this is not a new problem, because the moment you create file system, that actually means you need to allocate blocks to files. And that's why there are so many flavors, and I left 50 other flavors, of course. And these are not sacrosanct. These are design guidelines. So tomorrow, if you want to create a specialized operating system or even a file system for your custom-made software, you can create your own file system where you can have your own smarter file allocation method. We'll specifically talk about contiguous allocation, linked allocation, indexed allocation, and subcategories of that, which are actually used in MS-DOS, Windows, and so on and so forth. So let's start with the most basic one, which is contiguous allocation. So what is contiguous allocation? Before that, I just want to point out that whatever you come up with, like whenever you see a allocation method, you need to know whether it is good or bad. So these are the metrics that we will talk about. I'm not going over them in detail now. For each of the method, we will evaluate according to this matrix. And they range from whether there is internal, external fragmentation, whether they can be dynamically, like each file can be dynamically grown, the performance, of course, and of course, the ease of implementation. You don't want something very complicated to implement in such large-scale systems. So what is contiguous allocation? It's simple. You have a file, like I means I'm the user, you are the operating system developer, and what I would give is a file name and say, like, create this file. So contiguous allocation, what it does is that allocate files like a continuous memory, like basically allocate an array of blocks, contiguous array of blocks. Remember that your storage device is just an area, really huge array, 0 to n. Each element, 512 bytes in general in this lecture, it can go up to 4K bytes, but nonetheless, these are like 0 to n. What contiguous memory does, go from I to allocate I to jth block. Simple. Now, for that reason, like due to this addressing scheme, in contiguous allocation, you can just use base and limit register. Base is the starting address, limit is the size of the file. So essentially, if you want to allocate I to jth block, you store I and j minus I, the starting position and the number of blocks that will be allocated to that file. It's quite simple. Let me give you an example. So this is an example of contiguous allocation where, say, if we take the file mail, all you need to store in your FCB in the file control block, which will be part of your directory structure, is the starting position, in this case 19. That is, this file will start at 19th block, and then it will be allocated 6 more blocks after 19. Okay, and this is also provided in this diagram. This is a hard disk. These are blocks marked from 0 to 31. And out of that, this mail will start from number 19th block, go till 6 blocks, up to 24th block. So this is extremely simple, and it has its advantages and disadvantages. This is one of the very first file system allocation method that people came up with. So the advantage is it's extremely easy to implement. You just need to find a set of, like, start of a set of free blocks, assign a space. And it has low storage overhead. You just need to store the starting position and the size. And it gives fast both sequential access and random access, because it is one after other block. You don't need to traverse the blocks, go from block. You don't need to go from block 1 to block 100. You will always go from block 1 to block 2, or block 56 to block 57. So both sequential access and random access is also easy, because you want to have the third block of a file. You just take the first starting position, do a +3 and access that. So these are the good parts, and all these good parts come from this array-like abstraction. The bad parts, though, that comes from the fact that, think, if you're a user, you need to tell that what will be your final file size at the start. So essentially, you cannot grow your file. A file is specific at the very start. That actually might work for your custom-made embedded system, where you don't really let the users create files. Your operating system does everything. The moment you put user in the mix, you cannot really have contiguous allocation. Another problem is external fragmentation that some of you might have encountered in your assignment, which is basically the problem of holes. There might be like each file have an array chunk, like a set of array elements, contiguous set of array elements. And there will be holes between those objects, between those files. And those holes cannot be used later. Why? Because, say, the total number of blocks which are free are 100. And you want to create a 100 block file. However, those 100 blocks are divided into 100 small parts. You just cannot assign it, right? So this is called external fragmentation. The memory which is not part of any file are too small to allocate to a file, external to a file. Remember this. There will also be internal fragmentation that we'll see later. But external fragmentation essentially means external to any file, because that free space, those holes, are not assigned to any file. So to solve these problems, people actually came up with something called extent-based allocation. Okay. And what is extent-based allocation? Let me actually give you this sub-flavor, and then we'll go into another thing that you need to know about mapping. But let's actually have this flow. So what is extent-based allocation? It's simple. Instead of giving every single block, like telling like from block I, you go to block J, you divide your file system blocks into extent segments and assign those segments at one go. So you will never say that I'll give you 1 block, 2 blocks, 3 blocks, one after another. I'll give you 3 blocks at a time, 5 blocks at a time. And these blocks, these contiguous memory segments, are called extents. Very surprisingly, this extent-based file system solve this external fragmentation problem a lot, because all the holes are part of some other file. And you are giving extent, not specific blocks, right? That means the files can grow within an extent. Like you have already given 10 blocks, say if you have 10 blocks extent, you already give a file 2 extents, so 20 blocks. Let the file go up to 20 blocks. So just this simple modification or having set of blocks, name them as extent, and instead of block level allocation, you are giving continuous extent based allocation. A lot of problem is solved. And I feel it's beautiful. Like it is a great engineering effort where you see the workload and say like, if you just have blocks of memories, things work.
Yes. This contiguous allocation with big blocks.
Yes.
There's like frames.
There's like frames. Agreed. Like it is not rocket science, not out of the world, but the point is that it just solves problem. That's all. So what you do for a file is essentially have for each file, you will actually have a table with set of extent. Like the first extent is used and the second extent is used, the address of the beginning of the extent, and the extent size is sort of given on the operating system, so they know. Now the problem, any idea what is the problem with might be with the extent-based file system?
Space may go unused for
Fragmentation.
Internal fragmentation. You give the space, no one is using it. It's still wasted. When will this happen? When you have lots of small files. Lots of small files is a big problem for any operating system even today. 1 kilobyte, 2 kilobyte, 100,000 million files, your file system will break. So extent is great, but still have internal fragmentation. Okay, so contiguous, yes, go ahead.
If the file size is more than the extent, in that case, can I allocate more extents dynamically?
You would absolutely. However, that is for bigger files. So extent works wonderfully with bigger file sizes. For smaller file sizes, you have to always allocate according to extent. So most of the extent will remain unused. And no one else can use it because it's already used by your file. That is internal fragmentation. You allocate space, no one is using it.
Why is the size of the extent fixed?
Design decision. You can actually have variable size extent. People tried that also, but still according to workload, because you don't know the file sizes, you still have internal fragmentation problem. So in Veritas file system, where the extent-based file system was used first, the size of the extent was fixed. And after that, people tried larger sized extent, variable size extent, because then you also need to actually store that information, right? What is the size of that particular extent in your table? But still there are internal fragmentation, specifically when there are lots of smaller files.
Actually, that issue happened with the OS assignment, which had like a huge directory structure, right? You have to traverse it and sort the files.
Yeah.
Had like 1 million files, I guess. Very small, all empty, right?
Empty file is not empty because they actually take up your space. Directory will anyways be there.
It causes a lot of issues.
It does. It indeed does. And that's why the database systems, and they actually have special file structures where they merge everything into one and then have their own tables and all these things. Perhaps you will see that in your advanced, if any of you take the advanced operating system, they'll talk about file system a lot more. That's a big problem. Small files, a big problem. Okay, so far, this is actually your contiguous allocation system. And in contiguous allocation system, there is something that you need to know for designing an operating system, which is how to map. Remember that your user will never tell that give me third block. They don't know there are blocks. They will say read from third byte to 48th byte in the file. That is your logical address, LA. And from there, the operating system needs to map to the actual block numbers. Simple. Now in contiguous allocation, that is extremely easy. Why? So you just say that read the LAth byte. LA is logical, stand for logical address. Your block size is what? 512. If we just take a contiguous assignment, that means that you first need to go to the block where it which contain the LA byte, which will be LA integer division by 512. That is a block you want to read. And within that block, there will be an offset to reach to the LAth byte. And that will be LA mod 512. So what you will do, you will go to the Qth physical block and then read from the Rth byte. I mean, it's basically like straightforward because you want to read the LAth byte, everything is contiguous, so you don't really need to do anything else. Just go to that block and start reading from that particular byte within that block. And this is what I meant by simplicity of implementation. You know, even the mapping, you don't really need to do much. Do some division, like in one division, you'll also get the reminder and you are done. Okay. Now, as I mentioned, contiguous has problem with external fragmentation. So we try to do extend, it has problem with internal fragmentation. We want to do something better. So essentially, and I already talked about this internal fragmentation and so on, but essentially, the problem is solved by linked allocation. The idea is extremely simple. You had array. Array cannot grow. Array has problems. You go for a linked list. The same idea was used here. You come up with something called a linked allocation, which is essentially that each file is a linked list of blocks. And the directory entry is address of first block and address of last block, or you can actually optimize it by putting the last block to a null pointer, pointing to a null pointer, or putting a special value in the pointer. So what are these pointers? So essentially, let me, so pictorially, say file G have start at 9th block. And from 9th block, you read the data. Then in the pointer, you actually follow the 16th block. From 16th block, you read the pointer, you go to the first block, and you will traverse the list. Nothing special in it. You read the pointer value, it will traverse the list. So what is the pointer value? Pointer is a very memory construct. Now we are talking about file system. Abstraction is pointer still. It's something that points to a block, but it is basically a block address. The address of a block, address of the next block in physical memory. So that means that each block you need to set aside some bits to point to the next block, the address of the next block. Okay. What is the good part? You don't really need any compaction. You don't have any external fragmentation because there is no holes. You will always have the free block assigned to a file, the next free block. And files can easily grow, of course, and it's extremely easy to implement. But the downside is that you need to set aside some space in each block. That's a wasted space. But at least you don't have external fragmentation. The bad is, of course, storage overhead. Each block, some space is wasted. I don't think it's much. Many people don't think it's much. You don't think it's much, but it is much because now you have 1 petabyte memory. And suddenly you're just getting like 500 or 798 GB, 100 GB went for pointers. Just saying. And bookkeeping, not cool. Generally 80-90 GB going for file system is not unheard of if you have a 1 terabyte file system. So there is storage overhead, and then it's linear linked list. You have to traverse the linked list, read the address, go to the next address. So there is always this linear search problem. You cannot really compute random access. You can simulate random access, but still you need to traverse. It's a linear list search. You have to do linear search. You cannot do anything else. So it's complementary, and finally reliability is gone, or actually took a hit, because what happens is contiguous allocation. So one of your block is compromised. How? Well, you hit the block with a hammer, or more likely, possibly it fell from your hand. Happens to all of us. Your laptop fell from your hand. Some blocks got damaged. You cannot deny physics. In contiguous allocation, that will say like your file is corrupted, this block, you can still retrieve data. Now think like in pointer linked list, what will happen? One block got damaged, the pointer is gone. You don't even know what is next. Done. Your file is lost after that part. Does it make sense?
Even if the file is lost, like it's not even possible to free that space, right? So
No.
You can always find some block which is there, but no start pointer points to it.
Absolutely. Great point. So unreachability. Like garbage collection, you actually find the unreachability that no one points to that block. It has data, but no one is pointing to that block if you create a graph. So in that graph, those blocks are unreachable, you free them. Absolutely. And we'll talk about that in your in the extra concepts in recovery of file system. Okay. But it's still expensive. You have to create the graph. You need to do a DFS, find unreachability, mark and sweep and all these things. It is possible, Animesh. Absolutely correct. In fact, that's what file recovery systems do. But still, yeah, go ahead.
We're storing a special value at the end of file, then why are we storing the last block address like in the previous line?
Good point. So this is the
We are
implementation.
storing a special value in the 25th block and we are still storing the end block.
Not story and value.
So you can do either.
No,
The question is, that's a valid question. Why the last block? You can always surmise the last block. You're looking at a special value. It's just an optimization, the storing the special value. The original implementation was start and end block address. That's it. That was the original implementation. And that is sometimes useful if you want to read from the last block or something like that. Just giving you some, you start from the last block and then you follow the pointer like go before. You need some more bookkeeping and so on, like doubly linked list and so on and so forth. But otherwise, the basic implementation are start and end block. You can optimize it, remove the end block and put a special value in the end when you are just reading from the beginning to the end in those cases. Does it make sense? So basic implementation, this optimization, just as you told, special keep the special value, assuming that you will never want a doubly linked list structure with the previous block's address also. The previous block's address animation also solve the problem reliability a little bit. One block is damaged, but you can start at the end and then go back. Does it make sense? It depends. Yeah, go ahead.
So this system increases our access time. We do not even have discontinuous access, and we also lose a lot of fixed amount of memory just to save fragmentation.
It's terrible. I agree. However, that's why people came up with a modification called FAT. So we are still only midway. I'll tell you what actually is used, and I think it's a great data structure. Okay, but these are the concepts that you will use for that actual one. So linked list, not so good, but at least solve some of the problems for contiguous. How would the mapping work in linked list? So each file is scattered across the pointer. For accessing a file in a particular byte in that file, you have to traverse the linked list. No other way. Say if you want to read LAth byte, then each block will actually give you how much data, assuming that these parameters are either given in exam or in your design, or you need to assume it. Okay, and tell the assumption. In general, say if it's 512 byte block, then each block will have a 4 byte pointer. That means what is the data available to you? 508 byte. You want to read the LAth byte. That means the number of blocks in the linear linked list traversal, you want to stop after this many traversal. LA double division, interior division by 508. 508 is not a sacrosanct number. It's basically block size minus pointer size. How much data is in each block? And within that block, how much will you go? It's the same as before, LA mod 508, because you just need to go this many bytes within that block that finally you got to get your LAth byte. The only special consideration here is about the pointer size. So essentially you go few steps in the linked list, and within that block, you read from rth byte. So questions? One thing to note is that the pointer is stored at the beginning of the block in this structure. That means that if you want to read this displacement into the block, you have to also access for the pointer. So practically it will be r+4. First pointer you need to discount 4 byte plus r. Okay. Still, linked list is not. We are not happy with linked list. So Windows in 1977 came up with a structure. This is that old. Okay, these concepts are that old. So it came up with a structure called FAT that is still used today with different variations, FAT32, FAT16, all this file system. What did it say? It said that the main overhead here is basically a linear link search, right? So why don't you actually have a specific data structure in your file system called file allocation table, where each of the table entry will have address of the next block. So that file allocation table FAT state at the beginning of the volume, it has a specific, in the file system you need a specific address, relative address where the FAT table is stored. And in that, this table is indexed by the block number. If you have 0 to n, that there are 0 to n blocks, there are 0 to n entries. And each value of that array index, like the array value at that index, array I, is equal to the address of the next block. So how does it work? And at the end is specific EOF value, but I think pictorially it works much better. So essentially say you have a file called test, and the start block is 217. The file system will directly go to the file allocation table, FAT table. And its start is 207, so it look into array of 217. So array I, essentially, I is 217 here. The value at that array I is 618. That means the next block number of that file is 618. You go to 618. At that index, you see the next block number. Something is there, 319. You go to 319 and you continue. At the end, like the last block, we'll have a special value, generally -1 or null or generally EOF. However, EOF is defined, depends on the file system, end of file. So this is called a FAT file system, and it replaces the need for pointer in each block. You basically put all the next addresses and have a really nice data structure where the table is indexed by the block number, and each entry in that FAT is the next address of the next block. The last block, a EOF. So all you need to know, all the block, when you want to know all the blocks of a file, consult the FAT and read those blocks. This is better than linked list, I believe. It is still like this. Yes, go ahead.
Memory footprint is same. Instead of like n-1 pointer.
You are putting all the pointers in one place. That's all you are doing. Agreed. Ultimately, if you look in the table, forget about the index, it's like a bunch of memory addresses. You have to consult each one of them.
Storage overhead.
Storage overhead is the same. That is the main problem. And we'll say how much is the storage overhead.
Linear in number.
Let's see. So the thing is that you can actually modify this file entries, this FAT table entry sizes based on how many blocks do you need to access and how much can be each file size. You don't need a specific 32-bit pointer always. That's why I have given you an example here. See this. So if you have 512 GB hard disk, pretty common these days. And each block size is 4 kilobyte. Not 512 byte, 4 kilobyte. And your file system contains fat. So what is the smallest amount of memory used for fat for addressing the whole file system? This 512 gig. Remember, always when you do this sort of math sums, you'll always remember KB is 2 power 10.
128 MB.
128 MB into the pointer card size.
Yeah, into pointer.
Work it out. This is the answer. But yeah. So essentially, it will go for something like you'll find the 512 GB hard disk. That's correct, right? So 512 GB hard disk, you find the number of blocks, you got 227 blocks, and for 227 blocks, you need to power 27 blocks, 27 bits for each block. So you need at least this many, this size. So in this kind of sums, always have the number of blocks and then see how much you need, how much memory you need to address the blocks. I'll request you to work this sum out, but it's extremely simple once you understand that all you need to know is the number of blocks needed and then the number of bits needed to address that number of blocks. Cool. So I will request you to actually, like whoever is watching this lecture, work this out. If you don't understand, post in MS Teams, talk to us. This is important to understand because that is the main Achilles heel, main problem with fat, lots of space needed. Even though you can optimize better. So animation, yes, the pointer size, it will be like just putting together all the pointers, but you not always need the 32-bit pointers. However, your hard disk size is, you can actually work with that. Instead of 4 KB block, if you have 8 KB block, it will be reduced even. Understood? Now, the good is fast random access, only search cached fat in memory, because now you don't really need to go and back and forth in your each block. You don't know the next address. You just put all the fat, or at least most of the fat table in your memory, and then it is. Any idea how fast is RAM compared to disk access in these cases? 1,000 times. These guys, these SSDs that you guys are proud of, I'm also very proud of. They are like maximum read speed. Say it will give you what, 100 to 500 depending on the quality. RAM, a really bad RAM bought from like no-name company will give you 2.2 GB per second data transfer. I'm talking about really bad RAM and really good SSD. So essentially fat you can put into memory, it will be really, really fast. No question about it. The problem is the storage overhead for fat. You don't really want that. And the sequential access is again small because you have to do repeated fat lookup, but still in the memory, so it's not that bad a problem. I didn't put into red. So fat is your answer to linked allocation. It solves again, just like extend solves some problems, contiguous allocation. Fat solves some problem of linked list, sequential access. You put everything in a file, put everything in a table, put it into your memory, look it up fast. Expect questions on something like sizes of fat or some variations of fat. One thing to think about is might be, say, if you're given a fat size, fat 16 or 32, what is the maximum file size and what is the maximum partition size it can support? Not going to tell you the answer. It's very well known. If you search what is the maximum file size for fat, you will know the answer. But how, that is where the OS knowledge will come into play.
What's maximum file size?
Speed of access, and just so that the one file does not really take out the whole fat, because the fat size, the fat table size, I'll give you a hint. The fat table size is also limited. in most of the operating system. You cannot really let a fat table take 1 GB of memory. And from that limit, and from that limit, you will actually have limits on this access, like the number of the partition size or the file size. If you're a designer, what would you do? You will say that however big the fat is, I'll just incorporate.
Isn't the fat size always constant? Or if I have this amount of memory and this?
No, fat size is not constant. The amount of space reserved for fat generally is constant or within a bound. And that is when you format it with a particular fat system, it is reserved. So the fat can grow in that only.
The number of bytes are fixed now. How we want to distribute them, how many entries to keep is up to us.
And that's why there is a maximum size what a FAT32 can actually support. It cannot support more than 4 terabyte or something, I believe. Okay. Cool. So FAT, great, but still it is very much FAT32 came up in 1997, 20 years after the first FAT8 system came up. And after that, there is no FAT. People move into NTFS because, you know, they were like, this is not working. Like the more hard disks are getting bigger and bigger and you are changing the FAT specification. This is not working. We need something else. Similar time, Linux also came up with ext4, the ext file systems, 1, 2, 3, 4, Razor FS and all this. And we'll talk about now how they actually handle, and I think it's ingenious. So to know that what they did, we need to know something called indexed allocation. The idea of indexed allocation is actually fairly simple. The idea is that, so you have FAT, and this is a prime, think about it, in 1987, the first FAT came out, and the indexed allocation actually borrowed idea from there, because that was a good idea. They actually told that why do you need a whole separate file system space for FAT? Just store the table in a block and store that block's address in your file system structure. Whenever you want to read the blocks of a file, what do you need to do? You will look up the directory, the FCB, go to the index blocks, and then you traverse. So that actually remove the need for a whole system-wide FAT. For each file, they have an index block.
Normally, also like FAT would have been stored in somewhere in a disk only now. Wouldn't, so it would have been in a block normally also.
Yeah. But it is a file, it is system-wide, no? Like all the files will have one FAT. In
so
this
like
case.
but like the memory of the FAT is not separate, right? It's somewhere in the disk.
The memory means the space.
Yeah, the space.
Space?
No, not. I'm not talking about the total. I'm saying you said like stored in some of the blocks, like not separately, right?
Okay. I see what you're saying. No, basically setting. What I meant is that not setting up as a separate table at the beginning of volume and doing also bookkeeping.
Okay.
Everything is compute intensive. No, even when I was teaching, this video is stored somewhere. You have to read and write every single time, 100,000 times up to 100 in 1 hour. So instead of consulting FAT, you basically like go to an index block in the same file system space. No special place, no special lookup, bookkeeping, anything. And the schematic view is essentially that very simple. This is like extremely simple example of index blocks. We'll go into more details into 2 or 3 slides to show the ingenuity. But the point is that for each one of these blocks, these index blocks, each one entry in this index blocks will have an address to the actual blocks. For example, if your block size is 512 bytes, and each entry is 32 bits, 4 byte. That means you can address 2 to the power 32 blocks at most. That means how many blocks, how many actual physical file blocks can this index block address? 512 byte by 32 bits. 512 byte divided by 32 bits. Because each, like 512 byte is your index block size. each entry in that index block is 32 bits, and each entry points to a physical block. So in that way, you can actually, this is just an idea that index block actually also puts a constraint on the file size. That is the reason in any practical file system, any file system at all, you'll always have a limit on file size and partition size. Now let's see, I guess, any questions still then for index block? Because then we'll actually go down the rabbit hole and see the modifications.
So how's partition size?
So when you are saying this actual file box, right? These are blocks in the partition. It can be anywhere. That means each of the entries has to address anywhere in the partition. If it is 32-bit, you can only have 32 blocks at most.
So it's that one block per size, basically, when you say partition.
Block, no. Partition means the whole volume. Partition means the whole volume, all the blocks possible in that hard drive.
The number of partitions.
A partition is, okay, this is like a recap. So a partition is one file system, one partition. So it's basically whatever that file system commands, whatever storage blocks that file system can address. Yeah, swap is one partition. Like your C drive, like your D drive. Remember, one partition does not mean one hard disk. And hard disk can have two file systems, very separate ones. And each file system will address some blocks. Yes, you can. That's what partition manager is for. But this is not enough. People wanted bigger and bigger files. People also wanted smaller files. So they made modifications. But let's understand index allocation better so that we can go for modification. So this is the example of indexed allocation. The file zip has all you will store in your FCB is the address of the index block, 19. You go to the index block. You check the entries in the index block. In this case, there will be some entries like in 19th block, we'll have entries like 9, 16, 1, 10, 25. All it says that, well, the file's first block is 9. The second block is 16. Third block is 1. So how many blocks this file have? 1, 2, 3, 4, 5. 5 blocks. What are the minus ones? 3 blocks. Make sense? Simple. This is actually, if you think about it, it's simple. It's basically took ideas of FAT and put it into this whole index blocks, like repurpose it. Another good thing is that, so for FAT, you need to go from one index to other and so on and so forth. Like you go to index 1, then go to index 23, then go to again 5 and so on and so forth. Here it is, everything is contiguous. Like you will just read the bytes contiguously. The entries in the index block. Now, in index block, indexed allocation, you need to go to the index block. So it needs, so in the index table, using the index table, the mapping from logical to physical address is something, again, you need to worry about. Remember, the case is that the user wants to access the LAth byte. It doesn't know about block, doesn't care about FAT or whatever it is. How would you map from LAth byte to actual bit? Now here's the case. Say if you have a maximum size of a file in your file system, a file can have maximum size of 64 kilobyte. The block size is 512 byte and entry size is 32 bits. If you work this out, you would know, because you know the maximum file size and you know the block size, you know the number of maximum blocks possible for a file. And each of those blocks should be addressed by some entry in the index block. Each of them at 32 bits. So if when you calculate from these numbers the number of blocks in a file, multiply it by the block address, 32-bit, you'll get the size of one block. That means the index table can be in one block only. You have the maximum file size, again I repeat, you have the maximum file size divided by the number of blocks. That will give you the maximum blocks in a file. Each block is addressed by a 32-bit pointer. So you know the maximum size, maximum index size for a file, and it will come out to 512 byte if you work this out. Or even less than that. But that means that your file, the index for your file can be stored in one block. In this particular case, mind you, in this particular case, when there is only one index block, this is the mapping scheme. So if you have you have one index block, and that index block is just increased one after another 32-bit of address 1, address 2, address 3, and so on. Each address is for 512 byte. So how do you access LAth byte? You would first go into the index, take the value of that index, like where your LAth byte is, and within that 512 byte, which block is your LAth byte, and within that block you find the displacement. So the index array, the index of the index block, the array I sort of in the index block is LA integer division by 512, because each entry in index blocks is essentially 512 byte. And once you get that particular block value or block address, within that you need to go R bytes, where R is LA mod 512. This is a little bit different from the previous ones. Why? Because there you're talking about the actual byte going into the FAT or going into the linked list and so on. Here first, the Q, you will go into the index block, and R, you will go into the actual physical block. Let that sink in. So this is a very basic index block mapping where there is only one index block. Again, I repeat, one. There might be multiple. And we'll see them. The good of index allocation is it's easy to implement. It's essentially keeping a table in one specific block and storing that block's address into file structure. It's pretty easy. Files can be easily grown by adding more entry to the index block, but there's a maximum limit till the index block is not filled up. It has fast random access because you will just, when you look into the index block, you read it, put it into memory, you find the block size, and then you will just access it for random access. Fast. So when I say random access is fast, even for FAT or index, all I mean is that it's all in one place, so you can put it into memory. Linked, you cannot do that. You don't really know the next pointer values. The bad is the storage overhead for index, and meaning that you're basically losing one block at least, 512 byte for each file. And sequential access is slow. You have to again and again look up the index block and basically access those blocks. Now, I actually put the has a maximum limit in red because that is where people started doing modifications for indexed allocation. The first modification they did is that, one index block is just not enough. I have bigger files. What should I do? I'll have multiple index blocks and link them. Reserve one pointer in the index block, perhaps at the end, for the next index block. That is called a linked scheme. So the sole idea of linked scheme is increase the maximum size of a file. Instead of one index, you have now two index blocks. That means more and more addresses you can push in. What is the cost? You have to store the pointer to the next index block. So in link scheme, essentially there is no limit on size, and that actually solves one problem, index allocation. Yes, go ahead.
Instead of increasing the more index blocks, if we increase the block size, also we can accommodate more entries in the same.
You can. You can. But
How do we do that instead of?
people do that. But that will, pardon?
That would increase internal fragmentation.
But the file size is more. So
That is only for one file.
You have to also consider about internal external fragmentation. The bigger the file size, internal fragmentation block size, internal fragmentation will increase. Smaller the box size, external fragmentation will increase. Also, when I say internal fragmentation will increase, most think about now. That's actually a good question because that actually gives me a way to for my next slides. What if you have very small files? Most of the index blocks will go to waste.
is the block size same for all the files?
Yeah. That's hardbound. I mean, the hard disk is stupid. It just have a controller and some really basic device driver.
If they weren't, we would have to store the size also.
Yes. Ease of implementation is something that comes from physics. We can this some block
That
sizes.
would solve a lot of problems for small files. For large files, we can.
There are actually smarter ways to do that without going to the electronics guys and saying give me hardwares which I can have efficient different block sizes. Because ultimately think about it. If you're reading SSD, reading each block, reading each byte or each block has to be in the same way. So you need to have extra overhead to know that what is the block size. You need to store that and you need to compute that. That will add to extra overhead. So can there be, because and in operating system, it's not always only small files, only big files, only medium size files. It will be all over the place. You have to accommodate all for a good design. That's where the next improvements will come in. So there's a slight improvement, but this is not enough. This is the final one. I present you the final thing that generally people use, something called a multi-level index. Okay, simple idea. It's like paging. Yes, exactly. So directory goes to index block. Index block entry goes to more index blocks. Each of those entries can go to more index blocks. And at the final, so this, if you just invert it, it's like a tree. At the leaf of the tree are your physical blocks.
So, is it possible that for a file, the outer index directly goes to the file and for some it's more levels than file?
That's exactly what Linux uses ext4 onwards.
Does the force specify the number of levels?
Does the
Force specify the number of
4? Yes, 3 level at most. I'll tell you that. Give me a sec and we'll come there. Now, multi-level index first. Let's take one step at a time. We just learned about multi-level index. Let's look into two-level index. So two-level index is that each index block, so the FCB contains the address of the first index block, first level index block. Each of the pointers of the first level index blocks is address of the another index blocks. 512 byte block, 32-bit pointer. So how many index blocks can be there from first level? 512 byte by 32-bit.
128.
128? 2 power 8.
Bytes and this is
2 power 8, yeah, that's okay, correct. Yeah, there's a 2 power 3 factor that I also missed, yes. So yeah, 128, right? But each one of them can again go to other blocks. So here is a sum for you. What is the maximum size of files for two-level index with 4 KB sized blocks and 4 byte pointers? So each 4 KB index block, so what are the number of entries, like what are the number of blocks that you can hold? 2 power 10, address of 2 power 10. And first index blocks is 2 power 10 addresses. That means 2 power 10 index blocks. Each of the 2 power 10 index blocks, 2 power 10 more pointers to physical blocks. So 2 power 10 multiplied by total at the end, like at your leaf level, it will be 2 power 10 multiplied by 2 power 10. You have 3 levels, 2 power 10 multiplied by 2 power 10 multiplied by 2 power 10. So the last set of blocks is basically each one of them are 4 kb blocks. Each of your leaves are also 4 kb. So 2 power, in this case, 2 power 10 multiplied by 2 power 10 multiplied by 4 kb. 4 GB, 4 into 2 power 20, essentially. That is your maximum file size. Does that make sense? It's similar idea as your page, which again come from your tree idea. Trees are extremely important. I guess you get that by now in operating system. Now I have two sums for you actually. What will be the max? So now generalize it. What is the maximum file size for n level index with 4M byte block sizes and 4 byte pointer sizes? It's basically finding the size of a tree. Or finding the size of leaves in a tree, actually. I put the answer here, work it out, should not be a big deal. If the answer is wrong, let me know. The second one is find the logical file specific byte to physical dot mapping in the 2-level scheme, because now for the finding the LAth byte, first you need to find the index in the first index block, and from there you need to find the index in the second index block. Okay. Work this out. If you face any question, put in MS Teams, but this is important. Expect questions like this. You know how to do the addressing in 1 index block. Now do it for 2-level index blocks. Okay. Work this one out. I also put a hint, but hopefully it will help. Yeah.
So you mentioned 4 KB sized blocks. You mean the block size or the index block?
What is the difference between index blocks and a block size? Both are same. It's basically a block. Even the index block is 4 KB, na? Think about it. No one is creating a special block, special looking 8 KB block or 512 byte block for your index. Index is just like another block with some special functionality. Yeah. Yeah, go ahead. Should it be?
3 power n.
Work this out. Let's discuss.
Even the previous question, like it should be n only.
This one.
Like extrapolate, like use that formula in the previous question. It will give 2 into like
4 and n level index. Okay, let's come back here, but let's come back here about the answers. 4 per improve by n plus 1 is, you're saying it's wrong and it has to be what?
It was 4 KB's multiplication, right? So KB का 102.
He is basically saying that if you put this formula into the previous one, the answers doesn't match. That's correct, right?
Yeah, so n should be like n over there is 2 and m over there is like 1 KB. Yeah, 1 KB. Right?
1 KB.
Right. So it is 2.
Okay, yeah.
It is
2 raised to power 10 raised to power 3 instead of raised to power 2.
That should be
Exactly. So the answer is 4
Yeah,
into
right.
2 raised to power 20. This saying it is 4 into 2 raised to power 30.
Then this formula is wrong, I believe, because the previous one worked out.
N only.
m power n plus 1.
Yeah.
M power n.
Yeah.
When
So what would be the answer then? The
m power n.
m power n.
4 into m power n.
4 into m power n, not n plus 1.
When they say n level index, they mean that the actual index, like where the index tables are located, we have n levels, right? With those.
Right.
The last level is separated out.
Yeah.
So that is not counted.
Yeah. Because the last level is
It's
essentially
actually the file. So the number of pointers will be m into m into m into for n, so m power n.
m power n. Yes, because you are then multiplying it by the block sizes after that.
So that 4 wala factor, so we have multiplied only.
Yeah. So m power n, not m power n plus 1. Even this is not enough. So this is where the combined scheme come in. And thing is, this is nice, right?
The answer was correct. अब पता है
अब पता
That's what I was
वो
saying.
फाइल साइज का है ना. Okay, sorry.
That's what I was saying.
Sorry.
Whatever you say, again, I would actually request. So here's the thing. I worked that out and I actually felt it was m to the power n plus 1. This is something that I came up with. So if it is wrong, let me know. But if the last time I checked, it was.
That's what I said. It's 4 kb. Bytes.
Okay, so for the record, the answer was correct. Now work it out.
Yes.
Okay. So it will. Yeah. Now for combined scheme, 4K bytes plus block, 32 base address. Each of the index block will have some direct blocks, some single indirect, some double indirect, some triple indirect. ext4 has 3 levels at most. So in some cases, you will have direct blocks, meaning those addresses are direct addresses to direct file blocks. If that overflows, the direct blocks overflow. For example, this is like not many of these 32, not much space is reserved in your index block for the direct blocks. If this thing overflows, if your file size goes greater than direct block, you will go to single indirect block. What is single indirect block? It is the address of the next index table. If that overflows, you will go to the double indirect block, where it will be the address to a table whose addresses are also index tables. If that fails even, you'll go to triple indirect block. The address of it is the address of an index table. You go to that index table, each entry is another index table. You go to the index table, that is the entry to another index table. And finally, you have a set of blocks. You know why this is beautiful? Because it actually captures both, or actually all 3 types. Small file, which will only take the direct blocks, direct addressing. Medium files go to either 1 or 2 levels. Really big files, 3 levels.
Can I control which part of the file goes there?
What?
Direct block should be easier, faster to access.
Yes, direct blocks will be faster to access.
Can I control as a user that which part of the file is first?
No. There is a specific logic. Like first, you will fill up the direct blocks. If it is bigger, you go to indirect blocks. If it is bigger, you go to double direct blocks. Because you see, whenever you started, like you touched a file and created it, you don't know that it will grow up to 300 GB into next 2 months or 1 year. You cannot say that.
So the sizes of the direct, all the blocks fixed.
Yeah. Size of each block is like 4 KB, 512 byte whatsoever. The block size is fixed. Cannot do anything with that.
No, this length of the direct blocks single direct.
Oh yes, the number of bits are also fixed. That's a specification, right? That's why it's called a specification. Now work out what is the maximum file size that this can do. Assume the bit sizes, like if there is m bits, n bits, m1, m2, m3 bits, and the block size is 4 kilobyte. What is the maximum size?
We need the number of direct blocks count.
Yeah, m1, m2, m3. Take the number of direct blocks as, say, you'll have m1 direct blocks.
Okay.
Like parameterize it.
Okay. So we can also have multiple single indirects, multiple double indirects, multiple triple indirects.
Something around that, I think 8 terabyte or something. I forgot the exact specification in ext4, but it was like 8 terabyte file or something. It cannot hold more than that. 4 or 8. But check. Huh?
So how do they big files can you use?
How?
How do files bigger than that?
I recall, I am pretty sure 50 years back in another operating system class, a student like you definitely told, how could a file become more than 26 KB, 256 KB?
Yeah, but right now there are bigger files than that.
Not many. If hold on.
I'm pretty sure Teams server has big files.
Oh yeah. But these are like smaller, like each file size is 8 terabyte. If you say bigger file than that, you need specialized file system. More often than not, in real world, I would use basically object cache. I'll use something like Redis or even Cassandra to actually store these objects in bytes. I'll never use a file system for 10 terabyte files.
But like if you have files that big, then most probably you're not using a normal system, right?
No.
You only have big files in that system.
Example, very good point, Animesh. Can you give me an example where such thing happened in human history regularly?
What happened?
More than 8 terabyte, 10 terabyte files regularly.
Telescope observatory.
Hubble, yes. 3, Hubble, like space telescope, but not that much either, simply because the second one is the image of black hole. The third one and more that actually created a whole bunch of new systems is a Large Hadron Collider. Every second 10 gigabyte of data was generated. But in those cases, you don't really want a file system. You need some way to store that bits.
I remember seeing a video that CERN stores its data in like the magnetic caves.
I mentioned that actually. Yeah, that is the way you need to do it, magnetic tape, for this hard amount of data. But remember, these are like bits and bytes. It doesn't really have your file system. And even if you have that, it's a very basic one with some metadata associated with the bits and bytes. But that's a different engineering problem. So 8 terabyte is good enough for today. That is what I was trying to say. Okay. More than that, anyways, you are going to write a custom file system with basic functionalities and very fast seek and read write using some specialized hardware.
Making sense of so much data in one go is it doesn't make sense practically. So splitting it is always an option.
Sure, I don't know.
Terabytes of data together, like what can be like practical applications will be.
I agree. You need to make it more handleable to actually make any sense of it.
Okay.
I agree. I'm not disputing you. In fact, that's why ext4 still works. Perhaps in 10 years it won't. I don't know. AR VR is coming, right? And even normal people, like, just think about the amount of data that our nervous system generates. Talking to you, taking like this visual data, audio data, everything. The streaming that is happening in AR VR, like a high quality one, is astounding. For that, you might actually need bigger file systems. However, that should have, again, engineering challenges because that data is ephemeral and you don't need to store it. I'm not even going into details, but those are the spaces where machine learning and AR VR are the spaces where the new operating system advances are coming along. Okay. Cool. So you now know something cool. Combined allocation is the one that is generally used. NTFS sort of use it, but it actually have it has better file lookup capabilities. It uses some relation data structure and stuff. Now, lastly, which one to choose? The best method depends on the access type. Contiguous is great for sequential and random. Linked is good for sequential, but not random. So pick your choose depending on your workload. You can choose that. Indexed is more complex because you need more and more disk and file seeks. So that is mostly the problem. You go from index block to the next block to the next block, lot of disk reads, not good. That's why big files, copying big files is a pain. We all know that. Okay. We are done. We'll talk about very simply the free space for managing free space for efficient operation and talk a little bit about security in the first half of the next class. And then we'll move over to Saptarshi for a treatise on the last extra topic. Okay, so this sort of completes your idea of the file system mostly. The only one thing is left, which is your free space management. Like you have the free blocks that we put into file system. How we manage those free blocks, how to know where the free blocks actually starts. We'll talk about that very briefly in the next class. Questions? If you have more, please shoot. Okay, I'm stopping the recording. No, if anyone is there. Aryan was there and Deep was there and Suryam was there. Why didn't you guys speak up? I saw only one guy. So, any questions? I'm stopping the recording now.